In today's video, we're going to talk about a key concept in analog electronics called the slew rate of an op-amp. So what is it? Why does it matter? And how does it affect your circuit? Slew rate in technical terms is the maximum rate of change of the output voltage per some unit time. The slew rate of an op-amp is typically measured in volts per microseconds. Let's look at an example of slew rate limiting in action. To make this simple, I have a buffer op-amp circuit where the gain is 1 and no amplification occurs. My input signal is a square wave that goes from 0 to 10 volts in just 1 microsecond and periodically switches off and on forever. The slew rate of this particular op-amp is 10 volts per microsecond. If we compare the input signal in green to the output signal in red, we can see some immediate differences. Our input signal shows an almost instantaneous vertical jump from 0 to 10 volts. The op-amp tries to provide this instantaneous jump, but is unable to. It can only climb at a maximum slope of 10 volts per microsecond due to its slew rate. This is why the output signal climbs from 0 to 10 volts over the time of 1 microsecond. After going high for 1 microsecond, the input signal goes low for 1 microsecond and then immediately jumps right back up to 10 volts. Our op-amp tries to reach 10 volts as quickly as possible, but right as that happens, the input signal is already going low again. This is why the output signal is only able to stay at 10 volts for an infinitesimal amount of time before going back down again. This periodic pattern repeats, and you can see that our op-amp is barely able to reach 0 and 10 volts, hence the slew rate of 10 volts per microsecond. If our pulse signal goes from 0 to 11 volts, we can now see that the output is unable to keep up with that fast rate of change. This is known as slew rate distortion. If there is no way to change the input signal, you basically just need to buy an op-amp with a better slew rate. If you can change the input signal slightly, there are a few things we can do to avoid distortion. We need to either decrease the amount of voltage changed per 1 microsecond, or we need to give the op-amp more time to make that large voltage change. In our original example, we could have our square wave switch from 10 volts to 0 volts in 2 microseconds instead of 1, which allows our op-amp output to stay in an on or off state for a longer period of time, instead of constantly just barely hitting 0 or 10 volts. If we want to switch on and off every microsecond, we could also just make the on state 5 volts instead of 10 volts. This means the op-amp only has to provide 5 volts per microsecond, which is well within its max changing rate. Now, I used a square wave example to clearly display the limitations provided by the slew rate on op-amps. However, the same concepts apply for a sinusoidal voltage signal. In this example, I have a sinusoidal voltage signal. This signal oscillates from -1 volt to 1 volt and operates at a 1 megahertz frequency. The slew rate needed so that this signal experiences minimal distortion is the peak voltage times frequency times 2 pi. In this particular case, our slew rate needs to be at least 6.28 volts per microseconds. So when we run the simulation at this frequency, we see that the output and input are identical. However, let's say we increase the frequency to 2 megahertz. This means we would need a slew rate of 12.56 volts per microseconds to avoid distortion, which this op-amp unfortunately does not provide. Thus, the simulation of the output compared to the input shows some distortion. As we increase the frequency, the output begins to differ more and more from our input because the op-amp is unable to provide that amount of change in voltage over that specified amount of time.